Okay, before I forget, the problem set is due on, this problem set 8 is due class time on Monday. Of course, you can finish it wherever you are. I'll hold my office hours, my Monday office hours, in the morning rather than the afternoon. So from 9 to 11, I'll be in Alderman Cafe on Monday if you got questions. All right? Okay, so where I left off with was talking about air conditioners and sort of building the story leading up to it. Air conditioners managed to do a very remarkable thing. They managed to make a cold region in the midst of otherwise warm environment. Kind of a miraculous thing. If you think back to 200 years ago, the only way you could have cold on a summer day was to have stored ice from the winter, but suddenly you're now able to make ice during the summer if you like, and certainly to refrigerate your room. And the idea, the rules that an air conditioner has to operate in are these rules of thermodynamics, laws of thermodynamics, that the order of an isolated system is relentlessly, well, I would say relentlessly increasing, but of course it can stay constant if in the one extreme case. So it's at least never decreasing. But you can rearrange the disorder so that you can make an orderly patch within otherwise greater disorder. That's still allowed under the laws of thermodynamics, particularly the law of entropy. And that's what an air conditioner does. It makes a cold spot in your house at the expense of adding thermal energy to the rest of the world, and ultimately it's creating more disorder than it's creating order. And there are a couple of different ways of doing this. The classic way to do it involves fluids. There are solid state electronic coolers in existence, and there are probably a couple of other varieties of things that do this easily. But the air conditioners and refrigerators and cooling systems that you normally encounter use the same basic idea, which starts with the idea I was talking about at the end of last time, that if you compress and uncompress a gas, you can cause its temperature to go up and down, and you can use that to pump heat around. And I'll just rehash it a little bit, make sure you all are okay with the idea. And then add the complication that if you use a gas that is able to condense into a liquid, and then as a liquid to evaporate back into a gas, you get a bigger bang for your buck. So here's the basic idea again. So if we've got a trapped volume of air, which I do at present inside this syringe, I'm never going to be able to turn that air into a liquid, not in this environment, not in this situation. So I'm just working with a gas. If I compress it, and I do work to do that, its temperature goes up because I've added energy to it, and the only way it can manifest that energy is as thermal energy. It gets hotter. And if I uncompress it and let it do work on me, it conveys energy to me. Where did it get the energy from? Out of its thermal energy, so it gets colder. So it's as simple as that. I hope that makes sense. Compress it, it gets hotter. Uncompress it, it gets colder. And if you just do it in and out quickly, nothing really happens. You're back where you started from. I should point out that if you've ever worked with a bicycle pump, pumping air into your bicycle tire or into your car tire, it gets hot. And you might think, wow, that's friction. No, it's not friction. It's the work you're doing, compressing the gas, showing up as thermal energy in the gas, and bleeding out through the walls and making your hands, wow, that feels hot. Hopefully that's familiar to some of you. Certainly it was something that I encountered when I did a lot of bicycle riding. Okay, so how would you then use this as an air conditioner? It involves a lot of walking. You go outside, you then squeeze the gas that you got trapped. It gets hot, so hot in fact that the temperature, that heat flows out of it into the outdoors. And the gas then cools off again. It spiked to a high temperature, and then it settled back down to the local temperature, having bled away its heat. You come inside, and you expand it, you uncompress it. And when you do that, it gets cold. So cold that it's colder than the inside air. And heat from the inside air flows into that cold air. And then you go back out and back in and back out. And you are literally pumping heat. You're sucking it up like a sponge inside as you let the gas expand. You're almost sort of wringing it out, wringing the sponge out outside and back and forth. Any questions about that idea? It's a viable refrigeration scheme. And in certain contexts, it actually is used. Just a simple gas, compress it, uncompress it, compress it, uncompress it. All right. How can you get a bigger bang for your buck? Don't use just a simple a gas like air, which is called a permanent gas. It's very hard to turn air or the constituents, most of the constituents of air, into liquids. But if you start with molecules that are able to become a liquid, as is present inside one of these cans, you read about these things as compressed air. They're not compressed air. They are compressed gas, yeah. Well, no, it's not even that. They're a chemical that is liquid at room temperature when it's under pressure. Why is it liquid under pressure? At room temperature under pressure? It's because if you pack this actually has both gas and liquid inside. If you ever had a bottle like this, you know, you can shake it, right? If it were completely full of liquid, you wouldn't feel anything sloshing because it would be full. So it's got some gas, it's got some liquid. The balance between those two is struck when the density of the gas is high enough to replace any molecules that leave liquid for the gas. So there's a continuous exchange, but nobody's making any progress, right? And at room temperature, to get that balance, you have to have a pretty dense gas in there. So dense, actually, that it's above atmospheric pressure inside this can. If I release the pressure and let the gas expand and occupy the space that it would to be at atmospheric pressure, then the landing and leaving will be out of balance. The landing will be too slow. Not enough molecules in that gas now. It's a fluffy stuff. And the liquid will evaporate. Okay? So when you release this liquid, and I guess I hope you've all played with something like this, or a propane tank. All these things do the same thing. When you release the pressure and you let the gas become less dense, the liquid evaporates. Begins to evaporate like crazy because it's not, the returning rate is not fast enough for it anymore. And as the liquid evaporates, it gets cold because it needs the latent heat of vaporization. It's got to, evaporation sucks up energy, right? It sucks up thermal energy. So if you let this cat out of the bag, it will get cold as it turns into a gas. So far, so good? If you capture that gas and smush it back together to high density with some gadget, you'll get the landing and leaving rate to shift back towards landing being fast enough. In fact, if you crush it tight enough, you can get it to turn back into a liquid by making it so common that molecules hit the surface of the liquid and condense and become part of the liquid, that the liquid grows at the expense of this dense gas. So the background is, this stuff, when you release the pressure on it and allow it to become low-density gas, it evaporates. When you pile up the pressure and make the gas dense, then it condenses into a liquid. So you can control its direction of transformation from liquid to a gas or gas to a liquid. Whenever it goes from a liquid to a gas, it soaks up heat as the latent heat of vaporization. It's evaporating, getting cold. Whenever you condense it, forcing the condensation, it releases that latent heat of vaporization as it condenses. It's a chemical potential energy. It's just becoming thermal energy. It gets hot. So it's just like I had a question on one of these problem sets about why you burn yourself when you reach into steam, dense steam. Well, it's because it condenses on you and a whole lot of heat piles into your hand. So you can strategically cause this to go back and forth between a liquid and a gas by compressing and uncompressing it. So the little trick here now is to get this stuff into the syringe. They always say, don't shake, don't turn it, hold it upright. Well, okay, I violate the rules. I'm going to get the liquid out of the bottom. It goes in, boils like too fast. Stay there for a while. Okay, I trapped some. And I want to look down at this. This is the iffy part. Document camera. So we should be looking down at, there I am, yes. it got cold enough that it condensed moisture out of the room air. Now let's see, can you see that there's liquid in the bottom there? If I compress further, I ought to be able to turn almost all of this gas into liquid. And it's going to get hot in the process. And now as I expand it, it'll boil away. Is that viewable? A little out. Okay. And you can't do what I just did with air, because if you smash air that tight, the pressure is going to go up so much that it's going to hurt your hand. It's hurting my hand a little anyway. But I'm condensing all that gas into liquid. There it is, slosh, slosh. And then as I bring it out, it's going to boil. It's not super convincing. Anyway, it's happening. Ha! All right. If I let it all, it is boiling away now. Boil, boil, boil. Can I go any? I can certainly stop the boiling. Maybe if I zoom in. All right, zoom. Where's zoom? Zoom in. Okay. No boiling. Boiling in the tip. Anyway, I'll stop. But this is what happens. Now, I can now use it as a prop rather than as a viable demonstration, since it's too hard. Okay. Yeah. So now we can do the heat pumping trick a little more cleverly. We go outside with our gas. We smush it, and it gets hot, and it begins to, even though it gets hot, it still turns into a liquid. Lots of heat comes out of it. The heat that was my work, it used to be my work, and the heat that comes from condensing a gas into a liquid. Tons of heat comes roaring out of this side. This side's called the condenser, because we're condensing the gas into a liquid out in the outdoors. Any questions about that step? We then go inside with our liquid and let it evaporate by uncompressing it. Yeah. Still going, okay? And as it evaporates, first of all, it does work on me, so it needs that energy replaced. It gets cold for that reason. So it soaks up the heat to replace the work, to do work on me. And it also soaks up heat to evaporate the liquid into the gas. And then you go outside again, compress it, sort of wring the heat out of it, come back in, uncompress it. Is this all okay? You following it? And I'm going to let this stuff evaporate. Alas, it is a greenhouse gas, so I'm being a bad person here. All right, these are complicated molecules that are very dark in the infrared. Not great things to be spraying around, but it's for science, or education. So this then is, it's actually a dehumidifier, or it used to be a dehumidifier. Dehumidifier is a peculiar refrigerating system where the cold side's here, the hot side's there. They're within inches of each other, and they sit in the middle of your room. And that was the question I asked you last time as the opening for air conditioners. What happens if you put a window air conditioner unit in the middle of your room? It's basically this. And we'll come to it. I won't ask that question yet, but you can think about it if you like. This system has a continuous pipe that goes around in a loop. It's got a lot of turns in it, but it's basically one gigantic loop with a compressing device in the middle. That black object there is a compressor. And to show you how this works, let's follow the loop. Do I have a picture of the loop? I do. I'll point out that there are three components to that device. The same three components that are in your dorm fridge, that are in a fancier fridge, that are in your air conditioner, that are in your heat pump. They're all the same. The three components are an evaporator where liquid becomes gas, a condenser where gas becomes liquid, and a compressor that makes the whole thing work and consumes electric power. Okay? The picture of the parts. Where is it? There it is. Inside your house is the evaporator. Outside your house is the condenser. And the compressor, for technical reasons, is best located outside as well. So the fluid goes around in a circle. It enters, it enters the evaporator as a liquid, and it goes through a pressure release system, a device that just lets liquid arrive under high pressure and then leak through something and suddenly lose a lot of its pressure. It's losing pressure potential energy to thermal energy because of viscous effects. It's just throwing away its ordered energy and saying it went from a high pressure liquid to a low pressure liquid. Where'd the energy go? Thrown away. It wasn't a lot of energy. The liquid's not very energetic in terms of its motion. So it's suddenly liquid in a low pressure environment, it begins to evaporate like crazy because the landing rate is slow. It's low pressure, therefore low density. Any questions about that idea, why it's evaporating when the pressure goes down? Okay. So it evaporates, and as it evaporates, it gets cold. It's looking for heat to evaporate, so it sucks heat out of your house. That's the cold side. The evaporator side is the cold side. It's also the big side because to let it evaporate, you need room for it to evaporate into. So the evaporators are typically wider tubes. It's called a working fluid because sometimes it's liquid, sometimes it's gas, so pinning it down to one or the other is not appropriate. So it's a working fluid. And so the fluid entered as a liquid, it leaves as a gas, and it goes outside, and it then goes through the compressor, which has valves and stuff to make sure that the gas comes in at low pressure and goes out at high pressure. It's smushing the gas molecules together to build up their density. And as that happens, first off, there's work done on the gas, and it becomes hotter just by virtue of having work done on it. And also, because it's denser, it begins to condense. And so it's a double whammy. It gets twice, lots of heat comes roaring out of this compressed working fluid as it transforms into a liquid again. So it condenses because of the high pressure and density of the gas phase. And then it goes back through the constriction and does the whole thing over and over again. And ideally, that loop is perfectly sealed, so nothing ever gets out. The molecules stay in there for years going around the circuit, which always strikes me as kind of an amazing thing. They managed to trap the gas in a system with moving parts. The compressor's got moving parts in it. How they manage to keep the gas in is, they do it. So if I flip the switch here, what I did just now is I turn on the compressor. The compressor is now taking low density gas that comes in, smashing it. It's going out as high density gas that's quite hot. And that high density gas is quite hot, bleeds out heat into the room, and then begins to condense into liquid. So the compressor takes gas in here, it sends out liquid here. Well, it's dense gas initially. It's turning into a liquid as it goes through this finned structure here. The finned structure helps convey the heat to the air. So that's why it's got lots of little feathers on it. That's to help exchange heat from the condensing working fluid to the room air. So this is genuinely quite hot. I wouldn't want to hold it for any length of time. It's that hot. The fluid condenses, and it goes through this little teeny pipe. I don't know if you can. It's good. Anyway, this little teeny pipe, because it's very dense stuff. It goes into a little valve where the pressure is released, and it begins to evaporate. So this is the evaporator. It's filled. What comes into it is liquid. The pressure is released. It evaporates, and it gets quite cold. Cold enough. I could hold it for a long time, but it's freezy cold. And so this is cold. It goes back to the condenser. The heat comes out in the compressor, comes out in the condenser. So after class, you can come up and feel these two. This one's ice cold. This one's hot enough that you can barely hold it. It's pumping heat from this side to that side all day. And in a dehumidifier, why would you do this? What a silly machine. It's moving heat 1.5 feet to the right. Stupid thing. The reason is because this surface is so cold, it encourages room air, the moisture in room air, to condense on the surface of those coils and ultimately drip into a pan or some storage unit. So it's trying to get the water in the air to condense out, and then so it passes the air first across these coils to get the water to condense, and then it sends the air back across the hot coils where that cold air picks up the heat again and goes on to the room. There is a net increase in the thermal energy in this room. Why? Because this device is consuming electric power. And even if it were perfectly efficient as a motor compressor, there were no flaws in it. It was just built as perfectly as anyone could build it. It would still consume electricity because it is still needing to use the order in the electricity to move heat against its natural direction of travel. Moving the heat without consuming electricity would violate the law of entropy. But with the help of the electric power, which becomes thermal power subsequently, and therefore generates new entropy, it doesn't violate the law of entropy. So it's consuming electric power to move heat from left to right. What do you think is happening to the temperature of the room? How many think the temperature of the room is staying the same? How many think the temperature of the room is going down? How many think the temperature of the room is going up? Okay, it's a little bit split between stay the same and going up. If I put a space heater here, that is our toaster, and turn on electricity, what would happen to the temperature of the room? How many think the temperature of the room would go up? Right. This thing, if I put a box around it, and I put a toaster in there, you're all happy that the temperature of the room would go up. If I put the box around this and say it's a toaster, you'd say the temperature of the room would go, you watch electric power is going in, the temperature of the room is going up. You couldn't, where am I going with this? If I have two of them, two boxes, one's got a toaster in it and one's got this in it, they both consume the same electric power. Should they heat the room the same amount? Yes. It's an awkward story to try to, I got to give away my own question. The temperature of the room is going to go up when you run this guy. Why? It's consuming electric power, and the electric power isn't disappearing, it's becoming thermal energy in the room. This device is absorbing maybe 1,000 joules of thermal energy on this side, and it's releasing not 1,000 joules, but maybe 1,200 joules, because where'd the other 200 come from? They came from the electric company. They used to be electricity. They're now thermal energy. So the amount of heat it withdraws from the left side of the room and the amount of heat it delivers to the right side of the room are not equal. It delivers more heat to the right side of the room than it removes from the left side of the room. Is that okay? The result is, if you stir all the temperature, you stir the air up here and get rid of the differences in temperature, it's a net heater of the room. No different from a toaster. If this device is consuming 200 watts of electric power, it's heating the room the same as a 200-watt toaster, the same as a 200-watt space heater, the same as a 200-watt incandescent light bulb. I joked about the Easy Bake Oven, cooking food with an incandescent light bulb. Any device, your computer, if they consume 100 watts of power, and it doesn't send some of that power outside your house by, I don't know, but as light or sound maybe, it's basically, ultimately, the electric power gets ground up and becomes thermal energy in your house. And how the grinding up and all that doesn't matter. Once it's thermal energy, it's thermal energy. So if it's consuming 100 watts of electric power, it's releasing 100 watts of thermal power into the room. And the details of the device don't matter. Is that okay? So this device is releasing more thermal energy here than it sucked up from there. The added energy was electric energy. And this then brings us, any questions about that idea, those ideas? Yeah, Megan? The reason the temperature of the room is going up is because it's not exporting, in this case, any of the thermal energy outside. It's moving thermal energy from left to right, and it's adding what used to be electric power that came in through a little wire. It's adding that thermal energy to the room. So there's a net increase in the thermal energy in the room, and that's going to heat the room up. Is that okay? Let's suppose, so this is the air conditioner. Let's suppose that it's a winter day and you want to heat your house. Well, let's not worry about this device for the moment. Let's suppose you want to deliver 100 watts of thermal power. Again, a watt is a joule per second. So that's 100 joules per second of thermal power, thermal version of energy into your house. If your house is very little, that might be plenty to warm it up. Okay, so you want to deliver 100 watts of thermal power to your house. You got two choices for doing that. One is you go to the electric company and buy 100 watts of electricity and use a toaster or anything like a toaster and just turn that electric energy into thermal energy. That will, if you buy, energy per time is watts, so I'm flitting back and forth carelessly between energy and energy per time, which is power. But if you need 100 watts of power to heat your house, you can buy 100 watts of electric power and just turn it into 100 watts of thermal power with a toaster or anything like a toaster, your hair dryer, your curling iron, okay? Can you do better? Well, yeah, actually you can. Let's suppose this device here consumes 100 watts of electric power. That's the same as what you were just talking about, 100 watts of electric power. You buy the same amount of power from the electric company. But this device uses that power a little more cleverly than a toaster. This device uses that 100 watts of electric power to move, and this is hypothetical numbers, I'm just make them up, to move 900 watts of thermal power from the left side to the right side. That's reasonable. It takes 100 watts of power to do this special move. So 900 watts of thermal power gets soaked up here, and what's delivered over on the right side, the hot side, is that 900 watts plus the 100 watts of electric power that were used to operate the machine. So a total of 1,000 watts comes out of this side. So you're using 100 watts to you're leveraging the 100 watts. You're only paying the electric power company for 100 watts of electric power, but you're getting 1,000 watts of thermal power showing up inside. Any questions about that possibility? You're using thermal energy is common. It's everywhere. Don't just make it from scratch with wonderful ordered energy that's equivalent to work. Use your work to carry the thermal power to where you want it to be within the laws of thermodynamics. And that's what this kind of a device does. It can gather way more thermal energy than it needs electric energy to, it's an awkward sentence. I'm not going to be able to assemble it. So this device, as I've described it, and that's about right, can provide 1,000 watts of heating power to your house at the cost of only 100 watts of electric power from the electric company. Questions about that? This? Yeah. Where did the 900 watts come from? It came from outside, where the thermal power. I haven't described the story properly. There's a wall here. That's your house. This is outside in the story I'm trying to describe here. So you gather the heat from the outdoors. Even though it's cold, you can still gather the heat. There's plenty of heat in cold air. You gather heat from the cold air. You carry it inside with the help of that 100 watts of electric power you purchased. And what is delivered then is two parts. It's the electric power that you purchased plus the 900 watts you gathered. That's what a heat pump does during the winter. So it's cold days. You guys many of you are in heat pump land, or your families are, where they have device is exactly as I described. There is an evaporator outside gathering heat. The working fluid is evaporating outside, getting cold and sucking up heat from the outdoor air. It then carries that heat inside in the working fluid, where a compressor inside squishes it and wrings the heat out of it. So the heat that was gathered outdoors is released into the house, along with the electricity, what used to be electricity, that was involved in making the move. So, okay? So it's an amazing leveraging process. And what I didn't bring up, about now in the newspapers and probably on televisions, they'll start selling glorified space heaters. And for some reason, they always make it look like craftsmen who've carefully constructed, you know, the beards and the long hair. Oh, they carefully constructed this device, which they don't call a space heater at all. They say 100% efficient. You plug into the wall outlet and you buy 1,000 watts, it creates 1,000 watts of heat and all kinds of other glorious things to say about it. It is completely identical. Yeah, it's 100% efficient. That's called conservation of energy. And it is indistinguishable, regardless of how they describe it or tout it. If you put a box around it and you see 1,000 watts of electric power going in through a wire, you can't tell whether it's their crazy device or whether it's a 1,000-watt toaster or a 1,000-watt hair dryer, or they're all the same. They're all 100% efficient at turning electric power into thermal power. Is this okay? I mean, hopefully you'll see these ads and you can laugh at them, because they're selling conservation of energy to you. You can do better. 100% efficiency sounds like it's perfect. Wow, excellent, right? You can do better. This kind of a device where you're pumping heat can be 500% efficient, 1,000% efficient. At the cost of 100 watts of electric power, you can have 1,000 watts of thermal power show up in your house by pumping it. Any questions about the pumping idea? And why you end up with more thermal energy in your house than you bought electricity from the electric power company? This process of moving heat against its direction flow, it becomes harder as the temperature difference becomes greater. That is, if you, on a day when it's only lightly cold outside, slightly cold, and you want your house to be slightly warm, you're only moving the heat indoors against a small difference in temperature. And the laws of the act of moving heat from slightly cold to slightly warm creates a little order. That's why you have to pump it, right? Heat wants to go from hot to cold. If you move it from cold to hot, but just a little bit of difference in temperature, it makes a little order that you have to pay for by consuming order elsewhere, electricity. But as the temperature gets bigger and the temperature difference gets bigger and bigger, the pumping gets harder, because each joule that moves across that bigger temperature difference creates a lot more order than before. As a result, the bigger the temperature difference across which you're pumping heat, the less efficient the process becomes. The more, for fundamental reasons, you need to consume more electric power to move every unit of thermal power. So, heat pumps move heat in any direction you like it. An air conditioner moves heat out of your house to the outdoors. During the winter, a heat pump moves thermal energy from outdoors to indoors. Those devices become less efficient. The leveraging goes down as the temperature difference gets larger. So on a cool day when you want to carry heat indoors, it doesn't cost you very much electricity to carry a lot of heat indoors. But on a bitter cold day, where you're gathering heat in a very cold environment and trying to carry it indoors, it uses proportionally much more electricity to do it. Is that okay? You're creating more order in carrying it across that big temperature difference. So the public service announcement part of this is, in mild climates, which I guess technically Virginia is a relatively mild climate. It doesn't get super bitter cold for long periods of time here. Heat pumps are very effective. They'll save you a lot of energy and money compared to devices that simply turn ordered energy directly into thermal energy, either electric power or burning fuels. The reason for that is because the temperature difference between outdoors and indoors is rarely very big. And so these pumping systems are relatively efficient. The leveraging is great. You buy 1 unit of electric power and you get 3 or 4 units of thermal power making the move. In cold climates, in North Alaska or something like that, you can't do this very well. In principle, you can. You can use one of these pumps even if it's crazy cold outside and you want to carry heat inside. The problem is that you might only get a 20% boost on the electric power you purchased. So you buy 1,000 watts of electric power and you only get 1,200 watts showing in your house. Yeah, Neil? What would I classify as a large temperature difference? The temperatures here in Virginia rarely get much below freezing for any length of time. So 32 Fahrenheit, 0 Celsius. To your house, which maybe you keep at 70 Fahrenheit, 20 Celsius. So it's about a 20 Celsius move. That's mild. But if you're determined to heat your house to 80 or 90 degrees Fahrenheit, which some people are, and it is 0 Fahrenheit outside a lot, it's icy cold or 20 below. That's a big difference now. And somewhere between those two ranges of temperature difference, you go from it being economical to have a heat pump. That is, the cost of the heat pump itself and maintaining it, plus the cost of the energy, still is less than the cost of just buying energy and just turning it right into thermal energy. But by the time you get these big temperature differences, the Midwest where it's 20 below a lot, for weeks at a time sometimes, now the heat pump, first of all, you need a huge heat pump to do this because you need to carry a lot of heat in to maintain a warm house, even a moderately warm house in a minus 20 below environment. The heat's just leaking into your house like crazy. So you need to move a lot of heat, and you need to move it all the time because you're never getting a break, and it stops being cost effective. Furthermore, these devices are not perfectly efficient. There's theoretical efficiency, which they have to live under the laws of thermodynamics, and then there's the real story. You can't quite do as well as theory says. You might not even be able to do close. These guys are pretty good these days. I don't know what the energy efficiency, how far off ideal efficiency they are, but between the cost of the machine, the cost of the energy running the machine and stuff, eventually it stops being worthwhile to have a heat pump. And so like the colder climates where it's 0 Fahrenheit or lower a lot of the time, no heat pumps. Okay. Yeah. The nice thing about modern heat pumps is they also serve as air conditioners during the summer. So it's kind of you're sort of stuck. If you want, there is no way to make a cold house by burning fuel directly. You have to pump the heat. Okay? Anything else I wanted to say about air conditioners? Yeah, that's good enough. Okay, so that's the story of, I'll turn this guy off. That's the story about air conditioners. They are literally heat pumps. They are devices that under the living within the rules of thermodynamics, they manage to move heat from cold to hot at the expense of consuming order from elsewhere. They have to consume the order from elsewhere in order to not violate the law of entropy. And so, but they manage to get the job done. They become more efficient at moving heat as the temperature difference across which they're moving gets smaller and smaller. I'm just sort of summarizing what we just talked about. Everybody's on board with that so far? You can sort of run the whole thing backwards. Not like a heat pump becomes an air conditioner and stuff, but that you can use, the air conditioner uses ordered energy to move heat against its natural direction of flow. And that's the heat pumping idea. How about anti-pump? Let the heat flow from hot to cold, and when you do that, that makes entropy, right? I showed you that when you've got a hot object and a cold object, and you let heat flow from the hot one to the cold one, that creates entropy. You're getting rid of order. It is orderly to have a hot object and a cold object. So if you let them dribble over to the same temperature, you've lost order. You've made entropy. Is that okay? Well, what if you don't just let the heat flow from hot to cold? You do it cleverly. And instead of making lots of entropy, you make only a little entropy. What do you do with the missing entropy? Or how did that happen? It's because you divert some of the thermal energy, leaving the hot object, and instead of dropping it in the cold object as heat, you divert a little of it and turn it into work. If you do that conceptual idea, do I have this in a view graph? Let me see. I've got nothing up there. I think I just, yeah, okay. This is approximately it. So the story is about automobiles, but there are many of these devices that do this. They take heat that is flowing from a hot object to a cold object, and instead of letting it just go and just throwing up your hands and saying, I don't care, they systematically extract some of that thermal energy, divert it, and turn it into work. And that's possible. The law of entropy is okay with that, as long as the whole process doesn't reduce the entropy of the world. And examples of devices that do this, one of the early, well, no, they're all over the place, but let me get this guy going, because it takes forever to warm up. Okay, this is a little steam engine. Did it light? It lit, yay. So a steam engine is a device like I'm just describing. Let me name the device I'm describing. They're called heat engines. A heat engine is a system that takes heat flowing the direction it likes to flow, from hot to cold, and diverts some of it strategically and turns that diverted thermal energy into work. So a steam engine does it. A steam engine starts with hot boiling water to make steam. That's the hot object. If all you had was steam and everything was hot, you're stuck. You can't do anything useful with it. But not everything's all steamy hot. You got cold outdoors, or a lake, a river. So you got a hot object, you got a cold object. If you let heat flow from the hot object, in this case steam, to the cold object, the outdoor air, the river, the bay, that flow of heat from hot to cold, you can divert some of it and turn it into work. And now it's just down to technical details. How do you make a steam engine? There are a whole slew of ways to do it. An automobile does the same thing. It burns the gasoline. That act of taking chemical potential energy and turning it directly into thermal energy is akin to taking electricity and running a space heater. It's crummy. It's taking an ordered energy that's equivalent to work and turning it, bang, into thermal energy, which is not equivalent to work. Unfortunately, people have not figured out how to avoid the burning process. There are fuels with which you can avoid the burning process, where you stay ordered the whole way. Nothing ever gets hot. Nothing ever has thermal energy. But they're exotic fuels like hydrogen. Yeah, great. Hydrogen does beautiful things, but you got to make the hydrogen. How do you make the hydrogen? You still burn fuel. You're stuck. Anyhow, so what eventually should happen with this toy up here is that the water will begin to boil, and as the heat flows from the boiling water into the room, as it will, it runs a piston and gets things going, like the old-fashioned steam engine. And when I start to hear it whistling or something like that, we can zoom in on it. Another example of a heat engine is just Mother Nature. The Earth has in many situations, it's got hot spots and cold spots, particularly regions where there's land and water. The land heats up when the sun rises, much faster than the water, so it becomes the hot spot relative to the water. And so you got hot spot, cold spot. you can get some energy, some work done with this. What happens? The winds start blowing, and the winds blow from the hot goes up. The winds blow toward the shore as the shore heats up in the morning. Then when the sun sets, the land cools off faster than the water does, and now the buoyant forces rise off the water, the air flows offshore. So the winds reverse between the morning and the evening pretty regularly. And what's driving the winds? It's a heat engine. It's the movement of heat from hot to cold between these temperature differences on the Earth. And there are big scale, little scale heat engines going on in the Earth all over the place. Water moves around because of this, and you get hydroelectric power. Where'd the hydroelectric power come from? Heat engine. The whole atmosphere is lift the water up here, drop it off there. It's all about moving heat. Okay? Is this guy going to go? Yay! Okay, so look at. Yay! So it's doing very useful work, right? The little hammer going bang, 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 bang. There's steam coming out of the boiler that you see horizontally and all scorched with carbon. That steam is running the piston that you see on the left, the shiny object that's jiggling around. And that's spinning the wheel and pounding something on that pretend hammer. Okay? Steam engines, and why is it slowing down? Is it maybe running out of water? Anyway, I will stop it, otherwise something will go wrong eventually. But steam engines, in part, revolutionized the world. The Industrial Revolution, I think, was largely steam-driven. We still use steam for lots of things. Lots of heat engines run on steam. For example, most power plants, whether their source of thermal energy comes from burning fuels, in some cases from the sunlight, and then from nuclear fuels. They create a hotspot, and the hotspot boils water or makes steam, and the steam then runs through a system that extracts some of its thermal energy as work. All right? Where I'm going to go, and I'm not going to get very far in it, so let me just give you a piece of how efficient. Yeah, I don't actually want to do it how an automobile engine works. What I will do it on, I'll do it on Monday for both of you who come. And the automobile creates its own hotspot by burning fuel. It burns that fuel. It needs to then let the thermal energy in the burned fuel, which I sort of call the exhaust gases, I guess, the hot exhaust gases, it lets that heat flow out into the great outdoors. Consequently, an automobile engine should be somewhat more efficient on a cold day than on a hot day. You get a bigger temperature difference. Just as it was harder to pump heat from really cold to really hot than it was across a small temperature difference, you get more bang for the buck in letting heat flow from very hot to very cold. If you let heat flow from very hot to very cold, that by itself would create so much disorder that you don't have to make very much disorder. You could divert a lot of it, a lot of the heat, and turn it into work. So heat engines become more energy efficient, you get more leverage and more efficiency when the temperature difference is huge. So they don't just boil steam at room temperature or at usual open pot temperature. They boil the steam typically under pressure where its temperature is quite high, way above conventional boiling temperature. So they're using very hot, high-pressure steam to do the tricks. The same thing with the automobile engine. It burns the fuel and air to very high temperatures. It's making thousands of degrees in that puff of burned gas, and letting the heat flow from that very hot place to the outdoors, which is whatever it is. You could divert a significant fraction of that thermal energy and make work out of it. So we'll do that another day, but that's where we're headed.